has had its own list of impossible problems. We're talking about equations so tough that their solutions were thought to be completely out of reach. But what happens when a 200-year-old wall of impossibility suddenly gets a crack in it? Today, we're diving into a claim that could literally rewrite the rules of algebra as we know them. So it really makes you wonder, right? Are some math problems truly impossible? Is there some fundamental line that math just can't cross? Well, for a very long time, when it came to solving a certain type of equation, the entire mathematical world had a single unified answer. And that answer was a resounding yes. And that yes, well, it's been the law of the land for 200 years. Think about that. An entire era of algebra has been built on this one idea that certain really complex equations just don't have a general solution. It wasn't a theory, it was considered a settled fact. Case closed. All right, so let's get into the specifics of this so-called barrier. We're not just talking about some tricky homework problem. No, this is about a major theorem that drew a hard, uncrossable line in the sand, one that defined the absolute limits of what algebra could do. And here it is, the barrier itself, the Abel-Ruffini theorem, all the way back from 1824. Basically, what it says is this. There's no single universal formula using simple stuff like addition, subtraction, or square roots and cube roots to solve all polynomial equations once you get to the fifth degree or higher. That was it. A definitive line was drawn. And listen, this wasn't just some academic suggestion. It became a fundamental truth in mathematics. For generations of mathematicians, this theorem was the ultimate proof of what algebra couldn't do. It was the final word, a big, solid, unbreachable wall of impossibility. But what if that wall wasn't as solid as everyone thought? What if 200 years later, someone came along with a sledgehammer? A new theorem has emerged, and it's directly challenging that long-held belief. It claims to do the very thing that was deemed impossible. So let's meet the challenger. We're talking about Professor Murad Sultan Azwidi. His work, which he calls Azwidi's theorem, doesn't just try to find a crack in that old wall. No, it claims to build a bridge right over it. How? By providing an exact symbolic solution for a 20th degree polynomial. Yeah, you heard that right, 20th degree. And this quote, this really gets to the heart of it, doesn't it? It captures the kind of mindset you need to even attempt something like this. Professor Azwidi's entire project started with a simple refusal to accept the established limits. I mean, that's the very spirit of a scientific revolution, right? To look at a fact and ask, but is it really? Okay, so the big question is, how is this even possible? The key, according to this new work, is looking at the problem in a completely different way. So let's break down the major differences between the old school thinking and this new proposed framework. This table here really lays out the two different worlds. On one side, you have the classical methods where anything beyond a fourth degree polynomial is a dead end. Impossible. But then you look at Azwidi's theorem and it says, nope, exact solutions are totally achievable. The whole theoretical basis shifts too. We're moving away from traditional field theory to something called recursive structures. And honestly, the biggest change might be philosophical. It's a leap from accepting limits to flat out rejecting what he calls mathematical fatalism. So here's the crucial idea to grasp. The argument isn't that the old Abel-Ruffini theorem was wrong, it's that it was incomplete. Think of it like this. It perfectly described how far you could go with a horse and buggy, but it didn't account for someone inventing a car. The claim here is that with a whole new set of mathematical tools, that impossible destination is suddenly reachable. All right, now for the good part, the payoff. How does this new method actually do it? How does it solve an equation that we've been told for 2 centuries is unsolvable? Let's take a look at the process, in a nutshell. So the method isn't about finding one single magic formula that just spits out the answer. It's way more clever than that. It uses what's called a recursive process. The best way to think about it is like peeling an onion, layer by layer. The theorem is applied over and over, step by step, to figure out all the little pieces of the solution. And as you peel back the layers, these pieces build on each other until, bam, the exact roots are revealed. The key here is there's no guesswork and zero approximation. And this right here is probably the most critical point to understand. The result you get isn't some super long decimal number that's close enough. It's not a numerical approximation. What we're talking about is a 100% algebraic and symbolic solution. It's an exact expression, one that you can plug back in and verify perfectly with absolutely zero rounding errors. So, how exactly does it get around that 200-year-old wall? Well, according to the paper, it comes down to two key moves. First, it just completely sidesteps the limitations of something called Galois theory, which is the traditional way these problems have been tackled. Second, and this is the big one, it introduces a universal recursive formula that you can apply to a polynomial of any degree. That right there is a total game changer. Okay, let's zoom out for a second because the implications here are massive. This goes way beyond just one tricky math problem. If this whole thing holds up, it could represent a genuine paradigm shift in how we understand algebra itself. And here's why it matters so much. Solving that 1/20th degree polynomial, that's not really the end goal. It's the proof of concept, it's the demonstration. The real discovery here, if the claim is true, is a brand new method that completely redefines what it even means for an equation to be solvable to begin with. And this last quote, man, it really captures the sheer scale of the ambition here. What it's suggesting is that maybe no polynomial is truly unsolvable, that instead every single one of them is like a locked treasure chest. It already contains the complete structure of its own exact roots, just waiting for someone with the right key to come along and unlock it. And all of this leaves us with a pretty fascinating question, doesn't it? This whole story is just a powerful reminder that the limits of our understanding aren't always the limits of what's actually possible. It really makes you wonder, what other impossible walls, the ones we just take for granted every day, are just waiting for a new way of thinking to reveal that they were never really there at all?